Today we are going to talk about stereoscopic image processing or stereoscopic vision. And this will pretty much conclude the part of our course, which is about, so to say, pure image or camera-related things. The next topic that we are going to cover is about pattern recognition that in reality expands beyond the scope of just computer vision. The thing that we will be working with today is, in some sense, a pinnacle of what we could expect from this course in terms of the hardware-related stuff. So behold the stereoscopic robot. As previously it has 0 degrees of freedom, you can evidently tell that there are no servo motors here. And its main feature and the only goal of its existence is a couple of cameras that are pretty much aligned with the sticky tape. So in nearest future, we will see that they are not really completely aligned, but I bet that you cannot tell that by just looking at them. So we will have to check the frames that these cameras are going to give us. So we will calibrate this stereo pair. We will take a look at the frames themselves. We will realign them. Then we are going to obtain a so-called disparity map that is equivalent with a depth map, really. And after that, finally, we are going to get a point cloud with me sitting here and waving hands and doing stuff. So we will be pretty much aware of what's going on in the Sakhr robots with their stereo processing and stereo obstacle avoidance. In order to calibrate the cameras, we will first need to take several dozen of images of this checkerboard, this chessboard. Yeah, it's the same one that we have used previously, and I'm going to do pretty much the same stuff, except for saving 2 images at once. So when I press spacebar, 2 images by the names of number and then L or R will be saved to the drive. When you are going to reproduce this, please pay attention to the fact that we don't have any hardware timer here or hardware trigger. So please take images of only a static chessboard pattern, because otherwise the images will be off if we take them while moving at different moments in time. Well, that will do some harm. You can take maybe 30, 50 images. That will be pretty much enough. You can go even with the smaller number of frames, but the more you do that, the better. While we are calibrating our robots for football, we usually use some kind of, well, maybe 200 images or something of that kind. It gives us a reasonably good calibration quality. Okay, we'll hope it will work out. I'm rotating this chessboard all over the place. And pretty soon it will be enough, I think. So the calibration process here is threefold. The first one is the mono calibration of the first camera. The second is the mono calibration of the second camera. And the final part here is the stereoscopic calibration itself. So we want to understand the mutual positions of these cameras. We want to find out the rotational and translational matrices between them. And coupled with the regular calibration of each of the cameras, it will give us all the proper geometry of the frame. And we will be capable of obtaining the three-dimensional positions of all the objects in the surrounding, even if they don't stand or lie on the plane. That's the whole point of the stereoscopic imaging. So we have completed the obtainment of the frames, and here we have 36 stereo images, or 72 images in total. You can take a look at one of them. So here you can see that they are indeed misaligned, as I promised. They're misaligned by height. There's an offset in the horizontal direction, which is fine. And for sure, they are somewhat rotated. We will have to account for that. Now we are going to run the procedure of the stereo calibration thanks to this guy's GitHub. Check it out. So these are the images, and my computer is running through them. And seems like the chessboard is being detected properly on all the frames, which is good. So we are almost there. 32, 36. No, almost. Okay, so the order of the frames here in the alphabetical order. So the image number 9 is the last one. Okay. So what do we have here? Let's take a look. First, a list of the images, then the intrinsic parameters, cx, cy, fx, fy, all that stuff, or fx, fy, cx, cy, and 1. This is the calibration matrix of the first camera. Here, distortions, the same for the second one, and 2 matrices here. Well, the second of them is essentially a vector by the name of t. So here we have an offset of nearly 10 centimeters, which makes sense over here. And the offsets in the other directions are really pretty small. Here we see that it's smaller than a millimeter. I don't really believe that, but we can safely say that it's in order of millimeters max. And here we have just 5 millimeters of an offset in the x, y, z. Yep, so like this. This thing over here is rotational matrix. Here you can see that they are pretty much aligned, but not exactly. How can you tell that? Well, the values of on the main diagonal are almost ones, 0.999, all of them, which means that this matrix is almost an identity, but not exactly. Apart from that, we, as usually, have our TVX and RVX, as with the monocular calibration. So those are the positions and rotations of the chessboard pattern in the frame of each of the cameras. And we're pretty much happy with that. Great. So let's take a look at these 2 images. You see that they are not aligned in the z dimension. No, these 2. So my head is cut on the different height. And what rectification will do is it will basically align them. They're too big to fit on the screen, but here you can see that in terms of the height, it's the same. Those are clearly 2 different images because, well, take a look at the shoulder. Here it's different. So those are 2 images that were stitched in terms of the height. And now we can perform our magic of depth map obtainment or disparity map. Just to remind, what's that? As you remember from the lecture, we are calculating the distances by the way in which the object changes from the left eye to the right eye. So here the disparity, the difference in the pixel positions is big enough, and at the distance it's smaller. So that's the main idea, and using so-called block matching, we are finding that exact shift that brings a patch of the left image to the right spot on the right image. And now, with the rectified images, we can do precisely that. And here we have just a couple of things to do. So we have saved the parameters for the rectification on the disk, just in case something crashed and we need to restore it. And here, thanks to a blog post on Learn OpenCV and Adrian Rosenbrock personally. And yep, so let's take a look at the depth map. Here we have an image that is grayscale and small, and yeah, it's laggy. The thing is that this whole processing takes time, and my tiny little computer from 2018 is not really capable of doing it that fast. So you can see the drop in the FPS here, but that doesn't break the point. The point is that here we have our filtered disparity. So the raw disparity is a really noisy and messy thing, and well, we can show it, or you can take a look at it if you want to, or I even can show it right now. Yeah, let's do that. But the thing is that now try to compare the shape of me in the real frame and in the disparity. So the brighter the pixel is, the closer it is to the camera. There are some noises, of course, all over the place. But still, it's pretty much distinguishable. And now I'm going to try to change some settings, if this laggy thing will allow me to do so. There are multiple settings over here, and they represent the size of the window that is used to calculate the disparity, various types of filters. Yep, so let's check. Here you can see that as I increase the number of the disparities, the actual intersection of the two fields of view is becoming smaller and smaller. But with a smaller number of disparities, this whole method is not really working. It's not giving anything reasonable. So the next step that we're going to take is to visualize this as a point cloud. But first, well, you can try playing around with those parameters all by yourself. And now I'm going to show the unfiltered disparity. Disparity. Yeah, so you can see that here we have got an array of shades of gray. Well, apart from it not being normalized and shifted, nice and smooth from dark to white. The main problem here is that it's very noisy. So the origin of this noise comes from the fact that different pieces of the scene tend to appear differently from these two perspectives, from these two cameras. And because of that, we have to apply filtering that is capable of disregarding many pieces of noisy data. And as a result, we get this precious, smooth, not very dense, but still informative disparity map. And we're happy with that. usually we cannot reconstruct, so to say, the whole room in all the tiny details with stereo, just because it's a complicated multi-stage process and there are noises all over the place. So it's fine. And obstacle avoidance for our Sakar robots is necessary only in the closest neighborhood around the robot. You don't need to avoid an obstacle that's like 5 meters away from you. So it's pretty much fine. And another thing that I have to say is that these two cameras are full HD, so there are nearly 2000 pixels by x-axis in each of those cameras. And this means that at the distance of 1 meter, we have nearly 1 millimeter per pixel, nearly, which means that we cannot really rely on some elements that are smaller than that. So we are starting to lose texture, we are losing some tiny details here and there. And as the distance increases, the size of 1 pixel in the units of centimeters increases as well. So we either need some cameras that have a very high resolution, which makes the computational price of this whole process greater, or we have to use different types of lenses with a narrow field of view, but that's a problem from the other side. It means that we will have to scan all the field of view like this, moving the head all over the time. There are always trade-offs, and if you recall the lecture about the cameras, it makes sense to use a global shutter here because the shapes of the objects do not get distorted as they move. Here you can see that if I'm moving my hand, there's really no sense in this area over here. It's just some random mess and bursts of white. So there's an object somewhere and it's moving. That's all we can say. We cannot reconstruct its shape. We cannot say anything reasonable. And with global shutter cameras, we can do that. It's good that you're going to have global shutter-based robots as well. I don't know if you can hear that, but my computer is trying to cool itself because these operations, as I already said, are computationally expensive. So let's go further. And here we are going to do the following. We're going to generate a sparse point cloud. I think I have to, excuse me, I have to run through the code just a bit because I missed that. Okay, so here it's pretty much clear what's going on. We're just saving images. Here we have a class that contains a couple of main parts of the calibration process. Here we are extracting the corners and processing them. It's basically the same as we did for the monocular calibration. Then we are running this procedure, and it gives us all the data, all the parameters that we have talked about already. The next thing that is happening here is we are using these parameters newly obtained of the stereoscopic system to remap each pixel into the place where it is supposed to belong if the cameras are perfectly aligned. That is what's going on here. Well, then we're saving parameters, nothing special. And here we have a lot of track bars that allow us to change the settings. And well, yeah, here we read all of them. And the core thing that is going on here is this one. So we are passing two smaller grayscale aligned versions of the input images, and inside of this function, the block matching is performed. That's pretty much it. So this disparity thing here is the noisy image that I have showed previously. Then we are filtering it, and the filtering gives us the smooth and nice version of the disparity map. We are doing some centering, so to say. We're just making this more interpretable. And the last part is the visualization of the point clouds. So it's the same thing that we have had in the previous cell over here, but we have just added a couple of things. And let's go straight to this part. Okay, yep. So here we have ended up, somewhere here, we have ended up in the previous cell. And what do we have here is a call of this function. Scaled, this thing is a depth map that is just in the proper scale. And this matrix Q over here is a matrix that assembles the parameters of the stereoscopic system. So it has the focal length of the left camera, and it has the translation between the focal points of these two cameras. As we do that, we get an array of points in three-dimensional space, in meters, literal meters. After that, we filter them. Well, we basically filter the depth map so that if something is really far away, we will not see it. And we are visualizing just 1 point of 50 points, so we're going through the array with a step of 50 in order for us not to load the computer too much. And finally, we get the colors of the pixels that correspond to the points in the point cloud. Then we are coloring these points in the right colors, doing some updates with the Open3D library, and after that we are basically done. So let's run the code and take a look at what's happening. Yep. So here we have two versions of the same filter disparity on the left, and on the right, that's the best part. So I will allow myself to move slightly, which will result in some damage to the point cloud. But the thing is that here you can see, well, like we cannot rotate that, but you can see that those objects are in three-dimensional space. We are slightly inclined near this scene, so my palm is standing out of my frame, and I can show you what will happen with another object that I'm going to move. So here you can see. Okay, so it's not being shown properly. Okay, so let's do it here. It's noisy, yes, for sure. And it's not perfect by any means, but here you can see, for example, a nice feature that the chessboard is obstructing, it's overlapping, it's over me in the frame, so you cannot see my left shoulder over here, but you can see the chessboard. And this whole assemblage of colors is placed into this scene point by point. The important thing here that it's not just some distorted copy or something, it's just the three-dimensional points and the real three-dimensional model that we have calculated and that we are calculating at each step. That concludes our seminar, and the key steps for this stereoscopic vision part and the point cloud obtainment are the following. First, we have to calibrate the stereo pair, then we have to rectify the images, then we have to obtain the disparity map, and lastly, finally, we can calculate, obtain a point cloud, and we can get the colors that belong to certain places in the frame. So we can extract the colors of the points from the same input images, left and right. What we can do with that, we can do multiple cool things. First, we can create 3D models of certain objects. Second, we can apply some kind of pattern recognition. Let's say we can, as it's done in our football robots, we can, using the pattern recognition techniques, obtain the surface of the floor in three-dimensional space. And it's done by random sample consensus in the next lecture. So we can extract the real physical surface. Even if the surface is inclined, we cannot detect that by monocular vision anyhow. I mean, if there's a piece of flat floor and then something that is off from that flat floor. So we can reconstruct the real physical geometry of the world. We can, by excluding from the whole point cloud this floor, we can extract objects that stand out from it. And in such a way, we can detect the obstacles or opponents during a football game. Another cool thing that we can do here, it's not in this course, but still it's out there. We can feed this point cloud data into certain modern neural networks so that we can detect objects in 3D space. That's it for today. Thank you.